We are acquainted with the fact that gases exert pressure. Gaseous pressure drives this plane forward, and a difference in air pressure between the bottom and top of the wing keeps the plane aloft. Of course, airplanes are not the only massive objects which remain aloft in the atmosphere. Clouds may also weigh many tons. How can the water droplets which make up the cloud remain aloft? Let us take a closer look at the cloud. Here is a portion of a cloud viewed through a microscope. The random motion you are watching is called Brownian motion, after the British scientist who first studied it. Something must be jostling these droplets. Here is an object jostling about in much the same way. Turning up the light shows this object is being hit randomly by many small marbles, moving rapidly in all directions. Just as these marbles bombard the large object, pushing it this way and that as more marbles hit first one side then the other, so the random collisions with air molecules account for the erratic motion of cloud droplets. Since the force of these collisions with the molecules is large compared to the pull of gravity on a drop, the drops do not fall. Pressure in general can be interpreted in terms of random molecular collisions. And pressure differences, as in the airplane, can arise when more molecules per second strike one surface of an object than strike the other surface. We can study the behavior of gases in a pictorial fashion in this machine. Marbles are placed in it, and a vibrating disc at the bottom drives them in a vertical direction. They can strike on the bottom of this piston, which is attached to a gauge. When the machine is operating with only a few spheres in it, we notice that the gauge swings back and forth unsteadily. This is the result of the small number of random collisions per unit of time. With more marbles in the machine, the number of collisions per unit of time should be greater. The gauge reading should be higher. The pressure is higher. Now let's try a quantitative experiment with a real gas. We shall use this equipment. These bulbs contain carbon dioxide gas. They are connected through this stopcock, which is sealed off from the atmosphere. With the stopcock open, the pressure in the two containers is the same, half an atmosphere. Since so many molecules are striking each gauge per second, the pressure readings are steady. Now, Avogadro's law tells us that at the same temperature and pressure, equal volumes of gas contain equal numbers of molecules. Thus, with these equal volumes at the same temperature and the same pressure, we have as many molecules of carbon dioxide in here as in here. Now, what will happen to the pressure if we transfer all of the molecules into one bulb? This bulb, for example, thus doubling the number of molecules in it. Well, here's one way to do it. We close the stopcock first, then take some liquid nitrogen and place it around the tip of the bulb. The pressure in this bulb drops. The carbon dioxide is solidifying on the cold inner surface. Since the molecules no longer bounce around, the pressure drops to zero. Now let's open the stopcock. The molecules that were in here move into here, and they solidify. The pressure in the whole system drops to zero. All the molecules are now in this bulb. I'll close the stopcock, remove the liquid nitrogen, and replace it with water at room temperature. The solid will now vaporize into gas, and the pressure rises. All right, the solid has all evaporated and come back to room temperature. The pressure is now 1 atmosphere, twice what it was when we had half as many molecules in this bulb. By opening the stopcock, we can check this relationship between pressure and number of molecules. The pressure drops to half an atmosphere as the molecules redistribute equally between the two bulbs. These and many other experiments show us that pressure is caused by molecular collisions. Changing the number of molecular collisions changes the pressure. We have studied the effect on pressure of changing the number of molecules in a fixed volume. Let's now study the effect of temperature on pressure. In order to study the effect of temperature, we shall need a substance that remains a gas at low temperatures. From this table, we can see that helium boils at minus 269 degrees centigrade. Let's use it. It should not condense as did our carbon dioxide earlier. We have placed helium in this flask at 1 atmosphere pressure. Let's immerse it in boiling water. The volume and the number of molecules remain constant, but the pressure changes. The pressure is 1.24 atmospheres at 100 degrees centigrade. Let's put the bulb in melting ice now. And while it sits, record the data from the boiling water. At 100 degrees centigrade, we get a point here. Our gas was helium. Now let's record the data from the melting ice. The pressure in melting ice is 0.93 atmospheres. Let's take the container out and place it in dry ice at a temperature of minus 79 degrees centigrade. And again, while it sits, record our data. At 0 degrees, we get a point here. Now let's check the dry ice. The pressure at minus 79 degrees is 0.67 atmospheres. Now let's try liquid nitrogen at minus 196 degrees. For dry ice, we got a point at 0.67 atmospheres. The pressure at minus 196 degrees centigrade is 0.27 atmospheres. And notice, the helium is all gaseous. Thus, the data for liquid nitrogen give us a point here at 0.27 atmospheres. Now let's try passing a straight line through these points. We see that within experimental error, the line goes through all the points. Furthermore, were we to repeat the experiment with other gases starting at the same pressure, we would find that all gases give data which fit on this line.